The James Webb Space Telescope, JWST, is not only larger than its predecessor, the Hubble Space Telescope, but it is also equipped with advanced instruments designed to study the universe in unprecedented detail. One of its key capabilities is its ability to observe in the infrared spectrum, which allows it to peer through cosmic dust clouds and observe objects that are hidden from traditional optical telescopes. This capability is crucial for studying the formation of stars and galaxies, as well as for detecting and characterizing exoplanets. Unlike Hubble, which primarily observes invisible and ultraviolet light, Webb's suite of instruments includes the Near-Infrared Camera (NIR-CAM), the Near-Infrared Spectrograph (NIR-SPEC), and the Mid-Infrared Instrument (MIRI). These instruments cover a broad range of infrared wavelengths, enabling scientists to study a wide variety of astronomical phenomena, from the earliest galaxies in the universe to the atmospheres of exoplanets. Observing exoplanets and characterizing atmospheres is one of the most exciting prospects for Webb. Its potential to study exoplanets, planets orbiting stars outside our solar system, is significant. By observing these distant worlds in infrared light, Webb can analyze their atmospheres for signs of life or habitability. This includes detecting molecules such as water vapor, carbon dioxide, and methane, which are essential for supporting life as we know it. Webb's ability to study exoplanets extends beyond mere detection. Its high sensitivity and resolution allow scientists to analyze the chemical composition of exoplanet atmospheres in great detail, providing insights into their formation and evolution. This information is crucial for understanding the diversity of planetary systems in our galaxy and beyond. Unraveling the mysteries of cosmic origins is another key objective of the James Webb Telescope. By studying the earliest galaxies that formed in the universe, Webb aims to shed light on how galaxies evolved from their initial formation to the present day. Its infrared capabilities are particularly suited for observing these distant galaxies, whose light has been stretched to longer wavelengths due to the expansion of the universe. Webb's deep field observations, similar to Hubble's famous ultra-deep field, will capture images of some of the faintest and most distant galaxies ever observed. These observations will provide astronomers with valuable data on the formation of galaxies and the processes that drove their evolution over billions of years. Probing the formation of stars and planetary systems. In addition to studying galaxies, Webb is also poised to revolutionize our understanding of star formation and the formation of planetary systems. Dense regions of gas and dust, known as molecular clouds, are the birthplaces of stars and planets. Webb's infrared vision allows it to peer through these dusty veils and observe the processes that give rise to new stars and planetary systems. The telescope's ability to resolve fine details in these star-forming regions will enable astronomers to study the dynamics of gas and dust as they collapse to form stars. Webb will also investigate protoplanetary disks, the swirling clouds of gas and dust around young stars where planets are born. By studying these disks in infrared light, Webb can detect the signatures of planet formation and provide insights into how planetary systems, like our own solar system, came to be. Understanding dark matter and dark energy. Beyond its primary science objectives, Webb will contribute to our understanding of two of the most enigmatic components of the universe, dark matter and dark energy. Dark matter is believed to make up the majority of the mass in the universe, yet it emits no light and interacts weakly with ordinary matter and radiation. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. While Webb is not specifically designed to directly detect dark matter or dark energy, its observations of distant galaxies and their distribution throughout the cosmos will provide valuable clues about these elusive phenomena. By mapping the distribution of galaxies and studying their motions over cosmic time, astronomers can infer the presence of dark matter and its gravitational effects on the large-scale structure of the universe. Similarly, Webb's observations of distant supernovae and other cosmic phenomena can help constrain models of dark energy and its influence on the expansion of the universe. Collaborative efforts and international partnerships. The development and construction of the James Webb Space Telescope have been a collaborative effort involving NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. ESA provided the Ariane 5 rocket for the launch, as well as key scientific instruments and expertise. The CSA contributed the Fine Guidance Sensor, FGS, which plays a critical role in pointing and stabilizing the telescope during observations. International partnerships are essential for large-scale space missions like Webb, as they enable pooling of resources, expertise, and scientific goals. The scientific community worldwide has eagerly anticipated Webb's launch and is poised to leverage its unique capabilities for groundbreaking discoveries in astronomy and astrophysics. Webb's role in education and public engagement. In addition to its scientific objectives, the James Webb Space Telescope is expected to inspire future generations of scientists, engineers, and astronomers. Its ambitious mission and cutting-edge technology capture the imagination of people around the world, showcasing the possibilities of space exploration and discovery. Webb's educational outreach programs, developed in collaboration with educational institutions and science centers, aim to engage students and the public in the excitement of space exploration. These programs include curriculum materials, educational resources, and interactive activities that highlight Webb's scientific goals and achievements. By fostering interest in STEM, science, technology, engineering, and mathematics fields, Webb's outreach efforts contribute to building a scientifically literate society prepared to tackle the challenges of the future. All on account of its strong elements, this would provide us with a fuller image of the world as far as we might be concerned. Now, the best picture at any point seen was simply taken by the James Webb Telescope. Accompany us as we become familiar with the James Webb Telescope and how it could make everything different. Everything started after the telescope was first recommended in 1996. 3 gatherings of scientists and specialists from public and private sectors got together to check whether NASA could really construct the telescope. Each of the 3 groups reached the same conclusion: the telescope could be built. In 1997, NASA consented to pay for additional examinations to further develop the technical and financial requirements. By 2002, the organization had picked teams to fabricate the telescope's most significant hardware and formed an advisory group of scientists to assist with the design process. The telescope was formally named the James Webb Space Telescope that very year, in honor of the former head of NASA who made significant contributions to the development of the Apollo program. When engineers and scientists began building the Webb telescope in 2004, they needed to come up with new technologies and techniques to meet the mission's stringent science needs. Space travelers could fix and further develop Hubble while working from Earth, but Webb would need to do its work from too far away for Earth to be able to help. Despite these challenges, the team completed all 18 mirror segments and put them through rigorous testing to ensure they met the standards. It was eventually possible to visualize the telescope going into space and performing its job. The James Webb Space Telescope was built and worked on from 2012 to 2013. Different pieces of the telescope were being constructed in various places around the world. Building began on Webb's sunshield layers in 2013. These layers protect the telescope from excessive heat and allow it to function well in space. Over the next few years, Webb's various science instruments underwent extreme tests with high temperatures and shaking. Simultaneously, the telescope's 18 separate mirrors were carefully placed on its back plane. These parts were assembled and tested at NASA Johnson Space Center in Houston, Texas. In 2017, the telescope and its equipment also underwent one final round of environmental tests in a giant thermal vacuum chamber to ensure they would work properly when placed into space. Webb was finally sent into space around the Earth on December 25, 2021, at 7:20 a.m. Eastern Standard Time. How it functions. So how does the telescope truly work? People often make space travel sound too simple, so when you first hear about it, it might seem like just another camera. That is not the case. It is entirely different, which is why it took such a long time to get from idea to launch day. The James Webb Telescope is a powerful space telescope made to see things in space that are too cold or faint for traditional telescopes to detect. These are things like stars, galaxies, and planets that are beginning to form. The telescope is designed to capture infrared light, which is what these distant celestial bodies use to emit most of their heat. This allows us to study these objects in more detail. Infrared light cannot get through gas and dust, which makes it look obscured to our eyes. Webb, on the other hand, can see ultraviolet radiation as well as visible light and infrared radiation. This allows it to take pictures of things that are hidden by dust and gas, giving us a better view of events happening far, far away in the universe. It is also possible to study the characteristics of things on Earth, like their chemical composition and temperature, using infrared light. Infrared light is valuable in many areas of physical science and technology. It can help us learn about how stars, galaxies, and other cosmic objects are formed and how they evolve over time. It can also be used to detect signs of chemical pollution in our environment. The telescope has a large array of mirrors, advanced imaging and spectroscopy instruments, and cutting-edge thermal control systems that allow it to operate in harsh conditions like space, which, as you know, is very unforgiving. Because this camera is designed to go into space on its own, it had to be built to handle everything out there with no assistance. After the telescope was launched into space and separated from its launch vehicle, it unfurled and began its long journey to its destination, undergoing a complex series of steps along the way. There are 4 main steps. First, the telescope was positioned in a specific orbit known as the second Lagrange point. This location is approximately 1.5 million kilometers from Earth and allows the telescope to maintain a stable position relative to the Earth and the Sun. Second, it went through a process of unfolding and deploying its various components, including its large sunshield and primary mirror. Third, the telescope began the process of aligning its mirrors and calibrating its scientific instruments to ensure they were properly focused and ready for observations. Finally, the telescope began its scientific operations, starting with a series of test observations and calibration activities to verify its performance before beginning its full mission of exploring the universe. The James Webb Space Telescope's advanced technology and scientific goals make it one of the most anticipated space missions in history. Its ability to observe the universe in unprecedented detail promises to revolutionize our understanding of the cosmos and our place within it. As we continue to explore the universe, Webb will play a crucial role in uncovering new discoveries and deepening our knowledge of the universe's most fundamental questions.